Now we will talk about chain rule. What is this chain rule all about? So chain rule is a concept in derivatives which will help us to derivate the data if it is sequential in nature. So let's try to understand the chain rule. So we're talking about back propagation. So back propagation computes the chain rule in a manner that is highly efficient. So let us consider a function g where r is r, where r basically represents a function, and where y is equal to g of x and z is equal to f of y, and f of y basically is nothing but g of x. That's why z is going to be function of g of x. So basically what is happening, y is a function of g of x and z is a function of y. So we can see that it is actually incognitive. It is kind of linearly related across each other, and that's why if we want to derivate z with respect to x directly, it is not possible because z is dependent on y and y is dependent on x. So such kind of dependency is there. So z is a function of y. That's why if we talk about the chain rule of derivatives, so z has to be first derivated with respect to y, and then y has to be derivated with respect to x. This is how the derivation or the chain rule of derivative works, where a direct derivative of the data is not possible at all, and due to the dependence or the linear combinations of the functions over each other. Now let us assume that we have multiple paths for our data or the data nodes. So we have y1, we have x, then we have y2, then we have z. So if I want to derivate z with respect to x, so directly also it is not possible because z is in combination with y2 and y1 directly, but not with x. And that's how it is not possible to get the derivative of y directly. If I want to derivate y with z with respect to y1 or y2 directly, that is also not possible because z is coming due to y1 and y2. So z, if I talk about z is equal to y1 and y2. So if I want to derivate or if I want to do the derivative of y1, I have to first derivate y with respect to x as well. So what we will do is we want a derivative of z with respect to derivative of y1 plus derivative of z with respect to derivative of y2. But y1 and y2 are combination of the functions with respect to x. It is it is actually happening due to x. So y1 will be we need to derivate y1 with respect to x as well and y2 with respect to x as well, as both of them are the combination or functions of x. So if we see the multiple parts of this derivative, so dz by dx is equal to dz by dy1 into dy1 by dx plus similarly dz upon dy2 into dy2 by dx. So this actually tells us that the combination of this derivative is, even if it has multiple parts, we have to follow the linear partial derivative function or the chain rule derivative function. Now we will talk about the vectorization of this chain rule. So vectorization also is possible for this chain rule. For example, it can be notified or it can be represented in a vector form. For example, I want to derivate z with respect to x, which is directly not possible, but z is in linear combination with x. And this linear combination of x can be through multiple paths, or it can be through multiple levels as well. So for that I can represent it as dz by d partial derivative of these z with respect to partial derivative of x1 is equal to summation of partial derivative of z with respect to y1 and partial derivative of y1 with respect to xi. And in vector notation also we can represent it by having linear combinations of or vector combinations of or partial derivatives of z with respect to x1, x2, x3 and xm if we have multiple variables or multiple level of inputs. And similarly here also we can have the same formula will get replicated. Only thing is the x values will keep on changing, x1, x2, x3 and xm. So this is how the notation of an vector formation of your linear regression is. And it is actually, it can be denoted with the form of delta of xz, and which is nothing but partial derivative of y with respect to x, a transform of the partial derivative of y with respect to x into delta of yz. So this is how we can do the vector notation of the data. Now, vectorization and chain rule will try to understand what exactly it refers to be. So this is our denotation of our function, which is a chain rule or partial derivative function, which is given as a partial derivative of y with respect to x and transform of that vector value and into delta of y with respect to z. Now this partial derivative of y with respect to x is the n into m Jacobian matrix. Now this is actually a matrix value, this particular value, and we are taking a transformation of it. Gradient of x is a multiplication factor of Jacobian matrix partial derivative of y with respect to x with a vector that is the gradient partial derivative or delta of y of z. So we are multiplying this value with the gradient, and backpropagation consists of applying such Jacobian gradient products to each operation in the computational graph. So in the backpropagation, what we are doing, we are applying such Jacobian matrix or Jacobian gradient products to each level or the each operation in the computational network. In this general, in general, this needs not to apply to vectors but can apply to tensors. So we have tensors of values in a neural networks on which we are going to apply this Jacobian product of Jacobian product or Jacobian gradient products at each level of the neuron.